All right, let's get underway. I did post the key. If you've got questions about the exam, I would suggest you can see me. Normally I would say during office hours, but today I'm not part of the campus, so I go to get over the conference. I will send an email about that. You should come see me during office hours sometime next week. Take the time to read the exam and the key, and we'll discuss whatever issues or comments you want to make. Meanwhile, I want to continue talking about confidence intervals. We were looking at confidence intervals for means where we knew the population standard deviation sigma. It was what we were doing on Monday. Well, now I want to ask what happens if we don't know that standard deviation. If sigma is unknown, how do I deal with a confidence interval? I need a different distribution. If I don't know the confidence interval, I'm going to have to estimate it. Sorry, if I don't know the standard deviation. We have an estimator for standard deviation. What do we use to estimate sigma? Sigma is our population standard deviation.
You just use the samples.
And that's S. So if I'm going to use that, I'm going to need to figure out the way that's distributed. Well, we made some assumptions about it being normal. But the only way I can assume somehow that this is normal is to change my distribution. So if I can't use the normal distribution, I can't use z-scores, I need to use something else. Now the question is, what is the appropriate something else? So it turns out that the appropriate something else was developed by a gentleman by the name of Gossett. But Gossett worked for a brewery, and he was looking at different yields of alcohol for different yeast strains. He was working with very small samples. He only had 3 or 4 different samples at any given time. So he knew I wasn't able to make assumptions about being normal. And he said, I need a new distribution. He worked for Guinness. And Guinness didn't let their employees publish under their real names. So Gossett, W.S. Gossett, comes up with a new distribution. And publishes it under the name student. So what we get is a new distribution called the T distribution. And he says this is almost a normal distribution. But we're going to change it slightly. And the change is going to be dependent on how many things we have. So since he was working with very small numbers, 2 or 3 or 4 samples, he wanted to incorporate that. And so remember, we have this formula for the z-score. That's the formula for the equation of our normal distribution. We've never used that equation. That's why we have the tables and the computer and the Excel and all that stuff. He says, I'm going to adjust this based on my number of samples. And those numbers over there in the left column, these refer to the degrees of freedom for the way our tails are shaped. Take a look here on page 286 in our textbook. We see 3 different pictures. The normal distribution. In this picture, the normal distribution is taller in the middle and shorter out on the ends. There's less likelihood of being out in the ends in the normal distribution. In the t distribution, there's more out on the ends because he didn't know that it would be concentrated in the middle. It wasn't normal. So there was a larger chance of being out on the end. So he developed this red curve, which has further out higher tails. As the number of samples gets larger, as our degrees of freedom increase, these get closer and closer together. But in the t distribution, the tails are always bigger. Now that means confidence intervals get wider. T's give us bigger tails. But I need to know how to get this number. That number is called the degrees of freedom. We'll abbreviate it DF. And it's 1 less than the number of samples. So if you've got 3 samples, you have 2 degrees of freedom. If you have 10 samples, you have 9 degrees of freedom. If you have 16 samples, you have 15 degrees of freedom. And then we can use the appropriate PDF and CDF. Now, I must tell you, those PDF formulas that I showed you, that's just to make the pictures that we then have to do the CDF things with. The CDF formulas are even nastier than the PDF formulas. The CDF formulas are disgusting. I mean, there's the PDF. Look at how big the CDFs are by comparison. I'm never going to use these damn things, ever. I just wanted to show you the reason we're not using them. So, what I get instead is a new table. In the back of our textbook, Appendix D has a new table. And what this table gives me is it gives me the right end t-value for a particular area breakdown. The way this works is that I say, oh, I want a 90% confidence interval. If I want 90%, what's on the outsides? 5 and 5. This is one-sided, right? So if it's 90%, one tail is 5%, 2 tails is 10%, whether I'm looking at both ends or one end. But I can look at this information and then I can go down to the right number of degrees of freedom. Now, there are actually 2 columns here. This goes from 1 to 36 on the left, 37 to 50, and then it starts to skip by 5s. So once we get more than 50, this table isn't as good as we could be. We're better off using Excel or the calculator, and I'll show you how to do those in a minute. But even when these numbers are fairly big for our degrees of freedom, these numbers aren't quite the same as this last row. Hey, wait a minute. That says infinity degrees of freedom. What the hell? These numbers, 1.645, 1.96, 2.326. Where have I seen those numbers before? Right.
So as our number of samples gets bigger and bigger and bigger and bigger, we get closer and closer to a normal distribution. So in the long run, these columns get closer and closer to values we know. But as long as we are talking about a process where we have an unknown population standard deviation, I'm going to use this table instead of my normal distribution. Right there, I'm going to keep it close. Our formula for the confidence interval edges now changes. And instead of using z-score, we're going to use t. But notice, we're still taking the average, x bar, and then instead of sigma, we use s. We don't know sigma. We divide it by the square root of n, just like the standard error. I have that square root of n to account for the number of samples. I'm using t alpha over 2, just like you said, Mike, there's 5% high and 5% low. So I want to find that 5% number for a 90% interval. And then I multiply that by our standard error. An example. If I tell you that we have a degree of freedom of 9, or 9 degrees of freedom, and we want a 95% confidence interval, I'm going to need a t-value. So let's just start by trying to figure out which t-value we need. I'm going to do this 3 different ways for you. Let's do the first way out of the textbook. So I go to my table. And in the table in the back of the book in Appendix D, I say to myself, okay, 9 degrees of freedom. 9 degrees of freedom is here. I want a 95% confidence. Right at the top of that list, very top of the table, it says confidence level. I don't actually have to look up what alpha or alpha over 2 is. It's got it right here. If it's 95%, there should be 2.5 on each side, right? Which is 5% on the outside and 95% on the inside. So if I'm looking at both ends, that's 5% on the outside. Looking at one end, that's 2.5%. So it's this column. And that means I need this number right here in the middle, 2.262. I still am writing T sub 0.025. I wrote 0.025 because alpha is 1 minus our confidence interval equals 0.05. And then this number is alpha over 2. So that's where I pulled that subscript from. If I want t-values, I'm given the area in that tail, I'm given the area under the curve, right? That means I'm not actually using the z to find the area or the t to find the area, I'm using the area to find the t. That's our inverse. So on the calculator, when I go to do this same process, I'm going to look for a t with an inverse on it. And again, if I go to my distributions, lo and behold, right there on the first page, underneath normal, are my t's. And the one I use most often is exactly this one, that inverse t. So I'm going to go to this option, and I'm going to say, oh, I want a 95% confidence interval with 9 degrees of freedom. And all of a sudden my brain goes, wait a second. This inverse, just like the normal inverse, uses the CDF. So if I do a 95, that's going all the way to the left. And that means my tail has how much area in it? $95 on the left, how much is on the right? Is that what I wanted on the right? I wanted 2.5 on the right. Here's a difference. I need to tell the calculator 1 tail, not 2. So in spite of the fact that I want a 95% confidence interval, I need to make this number 975. Why? Because this is 0.025. That's the amount I want left on the outside. 9 degrees of freedom. I hit the paste button. And there's my 2.262. I have to know 1 tail to use the calculator, not 2. Now in Excel, I can do this there as well. I absolutely can do this exact same calculation in Excel. Let me go to my Excel setup. Here is a file in our examples for class group. And up here is that 2.62. And there's the command to do this calculation. T inverse, T.inv, but then it says 2 tail, 2t. If I say 2t, then I can give it the 95. 95 in the middle, 5% on the outside. So I can give it the 0.05. That's the outsides. The 2 tails should be 5%. And 9 for the degrees of freedom, and it spits out the right answer. If T.inv, you'll notice there's one without the number, without the 2 tail on it. That is one side. Now, the assumption here, we're using a CDF, it's going to give me the left side. When it gives me the left side, what's it going to give me? What do I need to give it for a number for the left side? 0.975. And then degrees of freedom, 9. Same number. So you use either one. There's also a version that only looks at the right side instead of the left side. So I could say equals T.inv.RT, which is right tail. And then what would we be putting on the right side? We'd be putting 0.25 with 9 degrees of freedom. Oh, no, they changed that one. Eek. equals T dot. They got rid of the inverse right tail. They have a distribution right tail. The updated Excel got rid of the right tail one. We can't do that anymore. Sorry, I have it written down from where I looked it up over the summer, and that was the way it said it worked, but nope. They got rid of it in the new update. So we'll stick with either doing both tails or the left tail, left side. Questions? I need to still get a confidence interval, right? This is just finding the t-value. Let me go back here. We just found the t-value. How do we actually make a confidence interval? Well, to make a confidence interval, I need another piece of information. I need to know the mean and the standard deviation for the problem in question. So let's take a look at problem number 21 here. A sample of 10 items is drawn. We don't know the population standard deviation. So we look at our sample, we say, hey, look, the mean is 270, and the standard deviation from our group of 10 is only 20. So we know the sample standard deviation and the sample mean. Let's make a 95% confidence interval. Problem number 21. I want a 95% confidence interval. I know that the mean is 270. I know that the standard deviation is 20, and I have 10 samples. The first thing I need to use the t-table, to use a confidence interval with S instead of sigma, I need degrees of freedom. What's the degrees of freedom in this case? We have a formula for that.
-171.
Aha. Which means I know the t-value to use with this. The t-value used with a 95% confidence interval and 9 degrees of freedom is exactly the t-value we calculated right up here. 9 degrees of freedom, 95% confidence interval. I know exactly the t-value to use. T 0.025 equals 2.262. So now I can say, oh, my confidence interval should be start at 270, add or subtract our t-value multiplied by the standard deviation over the square root of n. That's our number. This is our standard error. We take our standard deviation, divide by the number of things, square root of the number of things. That's our standard error. So let's actually do this calculation. 2.262 times 20 divided by the square root of 10. And I get this number, 14.3. I'm going to go 3061 here. You could just go 306. 14.306. And then we're adding and subtracting that to 240. Sorry, 270. I can read my own writing. If I subtract 270 minus 14.306, I get 255.694. And if I add, I get 284.306. So you told me the average was 270 and the standard deviation was 20 for your group of 10 samples. And I say to you, okay, I'm 95% sure that the real average is between 255.7 and 284.3 of the whole group. Not just this group of 10, but of the whole group. So I can estimate what I think is going on in the larger one by looking at the small group. Questions? What if I had 20 samples instead of 10 samples? What would happen to my confidence interval? What do I need to change if my number of samples goes up? My degrees of freedom is 19, and that's going to change my t-value. Aha. As soon as I change df, I need a new t. So what happens in my new t distribution? I need a new t-score. So I go back to my distribution. I go back to my calculator. I go back to Excel, whichever way you want to do this. I'm still using the 95%. So I can say, oh, 95%. But now DF is 19. I have a different number. And in this case, my table says 2.093. Now, if you did this on your calculator with your T inverse, distributions, inverse T, 97.5 is 2.5, 0.025. But now this changes to 19. 2.093. But now this calculation has a new number here and a new number there. $270 plus or minus 2.093 times 20. This time it's over the square root of 20 rather than the square root of 10. $2.093 times 20 divided by the square root of 20 is 9.36. So if I subtract, I get 260.64. And if I add, I get 279.36. Hey, wait a minute. A larger sample gave me a smaller interval. Why? This is true in general. A larger sample is going to give me a smaller interval. Why? That's exactly the correct answer. The more I sample, the better I get as an estimate, right? The bigger my sample is, the more information I know, the closer I should be to the right answer. So the bigger n becomes, the smaller this interval will get, assuming my mean for the sample and my standard deviation for the sample stay the same. This is where the trade-off occurs. The more I sample, the better my answer is, but more samples is expensive. I have to do more work. I have to deal with a lot more information. If I went up to 40 or 60, I could get a better estimate, a much smaller, be more confident that my answer is in here, and that would be a much narrower window. But I'd spend more money, I'd take more time, I'd do a lot more work. Questions?
So as for this one, as it gets closer to the actual population size, that will be more accurate than with the animal.
Sure, if I did the whole population, then I wouldn't be estimating anymore, I'd get mu and my standard deviation should be mu, right? I should know the entire thing.
So if the actual population is smaller, you wouldn't have to increase and as much to get like more accurate.
We're gonna have to figure out how to deal with what happens when the population is small compared to the size of our sample. Now, this is an interesting statement because we talked about this way back in chapter 2. We talked about what it meant for a population to be effectively infinite. It meant that my sample was less than 5% of the whole group. So if my sample is a larger percentage of the group, there's another correction factor that's got to go in here, which is unfortunately messy and is a pain in the ass. So there are statistical techniques that you'll talk about next semester in the quant business course that allow us to increase our population size artificially or increase our sample size artificially by resampling or bootstrapping or lots of other theoretical methods. This thing called a bootstrap method, there's a Monte Carlo simulation, all sorts of stuff. I'll leave that to Dr. Burns, he loves that. Other questions? So let's take a look at what happens more generally in Excel. Hang on. I have to pull up the problem I was looking at. Here it is, problem 25. Problem 25. Problem 25 says a random sample of monthly rent paid by 12 college seniors living off campus gives this set of information. This is how much they pay per month in rent. This is an expensive place. I want a 99% confidence interval. What's the average rent in this area? I only have 12 samples. My degrees of freedom is 11. And so really what I want to do is I want to try and get all this information. I don't even have the average. I don't have the standard deviation. Where am I going to get that crap from? Wait a minute. I've done this before. I've done this before. When I do this information, I need the information that is described. I got to do descriptive statistics. So let's highlight this information and let's go to that data tab. Data analysis. I'm going to click on that data analysis and I'm going to get my descriptive statistics. That's where we got the mean and the standard deviation and the standard error and all sorts of other information, that giant table of stuff. Descriptive statistics. Okay. I want the input here. It's a column. I'll create a new piece. Aha, I see something useful here. I see the word confidence level. I see summary statistics, right? But my summary statistics has a 95% next to it, right? I don't want 95%. What did I want? Book said I want 99%. Change that. There. It's going to do the lookup stuff automatically. I hit OK, and it generates this big new sheet that's very small, so let me blow it up. There's my mean. There's my standard deviation. And there's my confidence level. Okay, what can I do with this information? You'll notice I have this same information here, right? There's the same information we just got. So I'm going to go back here. This is the stuff we just made. I need a T level. Need my T value. Which way do you want to do this? Use the two-tail number, use the one-tail number. What are we going to use? I could do it on my calculator. I could do it on the table. I'm going to do it here because that's just easier. I'm already in Excel for all the other numbers. T dot inverse. We can use either number, either command. If I want to use the two-tail version, as soon as I hit the parenthesis, it tells me what to put in. Probability and then degrees of freedom. What's my probability here? What's in the tails? What's in the middle versus what's in the tails? 99% is in the middle, so the outside is? It would be 0.005 if I was just looking at one tail. That says two tail, so it's both of them, it's 0.01. And then degrees of freedom. We can compute degrees of freedom, but we can also have it do the computation directly. I can say, oh, there's a count right here, right? And degrees of freedom is the number of things minus 1. So I just say count minus 1. I just referenced the cell where the count was rather than type the number in. There's my T value. That is a very, very large T value. Why? Because we're looking at a very, very, very high confidence level. 99%, I really want to be sure. As a matter of fact, if I go to my table, 99% is the last column. 11 degrees of freedom, the book gives 3.106, 3.106. I'm perfectly happy with that. Now, I need to say, I want the average plus something, and I want the average minus something. Low end of confidence interval is the average minus t-value times the standard deviation divided by the square root, SQRT, of how many people. And notice I didn't actually type in the numbers. I used the cells that are highlighted there to refer to those values. And then I replace this same calculation for the high end by adding instead of subtracting. Average plus t-value times standard deviation divided by the square root of n. Hey, wait a minute. We said standard deviation divided by square root of n was called something. Standard deviation divided by square root of n is, we gave it a name. Not the margin of error, but the standard error. Hey, wait a minute. Standard error is one of the provided numbers. As long as I remember it's standard error, I can use that instead. They've given me the standard error. They've built that in. So I have a shortcut built in. Standard error already appears in my descriptive statistics. And notice, regardless of whether I use standard deviation or standard error, I get exactly the same numbers. Questions? So now I'm sure that my sample average rent was $1,812.50. I'm sure that the correct average rent in this area is between 1742 and 1882. Based off of these 12 samples. You used the phrase margin of error, Mike, and I really want to try and look at that more closely to try and figure out what margin of error really represents. That's going to take a little bit longer because there's something more to that idea. A mean with a known standard deviation for the population, a mean with an unknown standard deviation for the population. We had one other minimum variance unbiased estimator, and that was proportion. So I want to try and do the same thing for proportions. Where we're estimating the proportion of people who do a certain thing as an estimator for the actual population proportion. And P is the number of times we get what we want out of the number of things we sample. And the mean, pi, that's our proportion, that's some number between 0 and 1. And this number is going to be between 0 and 1 because you're never going to have more people do the thing than the people you asked. Well, it turns out I can say the exact same thing here. There's a central limit theorem for proportions. As we sample larger and larger things, this starts to look like a normal distribution. And that means I can use z-scores for dealing with proportions. And I will end up with the exact same formula. That I take the sample proportion, I take the z-score for the right error confidence level, and then I multiply by the standard error. Ah, what's the standard error for a proportion? Well, it turns out this standard error for a proportion is directly calculated from my sample proportion. That also looks like my standard deviation function, where you took a bunch of stuff, added it up, multiplied, and then took the square root. Same idea. So again, I have a huge advantage when I am dealing with a sample for proportions. This allows me to do things like the binomial. Remember, our binomial worked like this. So I can say, oh, our binomial has a proportion. What was the exam question about ordering light beer, right? 30% of people come to the bar, order a light beer. Well, that's 0.3. That's our population pi proportion. That's 0.3. But if I didn't know that in advance, I could say, all right, let's watch the bar tonight and see how many people come to the bar and order a light beer. Then I can estimate and get a confidence interval for the real proportion. On page 294, there's a table 8.5, which tells me about a minimum sample size, because I'm making the claim that as n gets larger, we get towards a normal distribution. That's what our central limit theorem tells us. Our central limit theorem tells us things get closer and closer to normal. But the sample sizes have to get pretty big. When these proportions are small, we need pretty large sample sizes to assume that we are dealing with normal behavior. If my proportion is around 50%, well, then a sample size of around 20 works to be confident that we're close to normal. But most of the time, it's upwards to 30 until we get to really small percentages. And then we really have to start looking at a large number of samples to determine whether or not something is normal. We're making the assumption a lot that our sample sizes will obey this. So again, our confidence interval is going to depend on our sample size, our sample proportion, and our confidence level. I think I can start thinking about margin of error based on this. And this makes more sense for me to think about margin of error. Because when we think about a survey, hey, who are you going to vote for in the next election? Then there's some sort of give or take to that, right? And our confidence interval is related to that margin of error. But if we want a particular margin of error, I need to be able to figure out what n I need. So we'll work on that on Monday. And we'll do a little bit more about the finite population idea. And we'll keep going from there. Thank you all very much. I hope you have a wonderful weekend. I will see you all on Monday.